seconds.
Right. All right, is that working? Yep. All right.
Sounds good. All right.
No circles plus one. Still got the
Yeah.
minus ones.
But mine work.
Oh,
Look at that.
click.
You can actually click one.
That's what they're supposed to say.
All right. So second speak today is because Franz, his supervisors are Shannon and Thomas, and he's talking about exploring agent dynamics. Take it away.
All right, so essentially what we're doing is we've got an agent-based model. The problem that we're looking at is broadly, why do these animals, so such as like birds and fish, which we kind of rank as having like a low intelligence, why do they do kind of like highly intelligent things, or at least what we could deem highly intelligent things, such as like milling and following each other around, and they're not clearly like communicating with each other. Especially in like the case of a fish, it's not saying like, hey, let's all do this for a second. There's kind of some underlying reason for why they're doing that. So the problem that we're exploring is, why is that happening? The first kind of thing we're going to do is we're looking at two different models, and then we're going to use game theory to kind of combine those two models so that they're running at the same time, and agents are going to be able to pick which model they want to gain some sort of benefit. So the first model we're looking at is the Couzin model. Essentially what it does is we take different interaction zones and then we respond differently, or an agent will respond differently based on the neighbors in each zone. So the first zone is the zone of repulsion. This diagram here, you've got the direction that an agent is going, and it's just a point particle. This zone of repulsion is essentially if there's other agents nearby in this area, I want to move away from them. It's kind of biologically motivated by having your own like personal space, or in case of a fish or a bird, actually existing, not being a point particle. The next zone is the zone of orientation. Agents that we find in this zone, we're going to want to align ourselves with them, so go in the same direction as them. As you can see, we have a viewing angle, so it's not just full 360 around us. For the zone of repulsion, that viewing angle doesn't exist because we assume that you can feel if someone's behind you, like touching you, but you might not be able to see behind you. Typically, we're using about 270 for most of the actual simulations, 270 degrees. And the last zone is the zone of attraction, so agents in this zone will go towards. I think I've got an example here. So we've got this agent in the middle, no one's in the zone of repulsion, and we've got three agents kind of heading in that upward direction, but we've also got a cluster in this bottom left. And so the way that you would kind of, the way that the model runs is it chooses an intended direction that it wants to go in the next time step. So this agent will kind of assess its local area and then choose an intended direction. But again, biologically motivated, it's not just going to be able to turn a full 360 degrees in one time step, so it has kind of an angle that it's limited to. So here we'll see, this is kind of the influence of the agents in the orientation region. This is the influence of the agents in the attraction region. Add them together, and this agent will want to go kind of behind it. Again, this is also a unit direction that it's looking at, so obviously if you add those two vectors, it's not going to be that length, but we take the unit vector of that direction. But it's not going to do that either. It's going to kind of go counterclockwise. So its actual direction will be this way. Right? So that's the first model, kind of an explanation of how the first model works. And so these just happen over a certain period of time, and each agent will assess its intended direction and move towards that intended direction. They all move at constant speed, so they'll just take a step in their direction that they currently have. There's three major kind of behaviours that we see from this. So the first one is swarming, which is, I've got a video here. So you kind of have, you have some group cohesion, but they're not kind of doing anything interesting in terms of, they're not milling or anything like that. they do stick together, so those kind of conditions force them to stick together, but there's not really that much of a higher behavior that we see. They kind of just want to stay in the same area. Another behavior that we see is this parallel movement, which is everyone kind of taking the same direction and just moving together as one group. Yeah, so could be interesting, but the most interesting that we actually see from this is something called milling, which is essentially all of these particles rotating around a core. And again, they're not really communicating with each other to do this, but just based off those kind of simple rules, they will eventually kind of just spin around this location, right? So this mill can move around and things, but that's the most interesting behavior that we've deemed from this model. And so when we talk about combining the models later, all of the parameters will go into trying to replicate this Couzin model. So if a particle is chosen to do Couzin as its model, then it'll be operating under parameters that have these conditions, or that lead to those conditions. So the next step, or the next model, is the selfish herd model. This model is taking Hamilton's kind of selfishness idea, which is essentially just if these agents existed in the wild, so in this 2D space, what their goal is to minimize the area that they own in case a predator would attack, and then if they have a smaller area, then there's less chance of them being eaten. The way that we do this is through Voronoi cells. So obviously in this kind of case here, the Voronoi diagram is just kind of this straight line. So the top part, the top agent will own that area of this plane, and then the second part, this bottom part, the other agent owns. What we actually do is we bound this, right? So we don't want these agents to think that they have an infinite area. We kind of give them a radius in which, okay, you're actually bounded by this kind of area, and we call it a bounded Voronoi cell. In the case of 3 particles, you would kind of take that as that, yeah, that's the bounded area, I guess, for that particle there. And so the way that this model works is agents, again, they have a direction and they have a position, and they sample the area around them. In my model, we've got them sampling in that vision cone, so the same as Couzin, and they sample each spot and they go, if I was to move to that spot and everyone else was to stay still, what would my area be? And then it kind of calculates all of the new areas that it would get, and it moves to the one that's the smallest, right? It works a little bit differently because in the original selfish herd kind of 2D adaptation, the particles aren't point particles, that they actually exist in space. But here we're assuming that they're point particles, and to kind of counteract this, we, instead of saying give the smallest area, which would just be like 0, we give them a target area to kind of hit. So it would be in, you could say like a target area of 100 units squared, and so they'll try to move in a way that's going to minimize, or that's going to get them closest to that target area. And so here we've got a kind of Voronoi diagram of all these kind of particles, and it's all bounded. And so each individual kind of particle has an area, and they would move to try and minimize this, or to try and get as close to a target area as they can. So with this in mind, this is roughly what those particles look like, right? So again, it's kind of like the Couzin swarming. There's not any like super high order behaviors, but they are sticking together, which is the main thing. Here I've got 100, and you can actually see the cells. And so as you can see, you kind of have everyone spreading out and trying to create space in the middle, so all the agents are kind of moving out, and then no one wants to be on the outside. Everyone wants to be on the inside of the group because that's where it's going to be safest. And so particles kind of move with that intention. So the next part was to assess the static case. So what I mean by the static case is we're not changing models just yet. We're saying so say on this diagram here, you've got 0 selfish herd particles in the first kind of area, and what happens is we're recording 100 particles moving in this space. 0 of them are selfish herd, so it's just a full Couzin kind of regime, and we're recording these 2 parameters that we care about. One is the local rotation, which is an indication of milling for Couzin, and then the other is this average delta DOD, which is basically how close am I to my target DOD. What we see here is as we're increasing the number of selfish herd particles, so it's a constant amount, so as we're kind of increasing the proportion of selfishness, we see kind of just a general trend that the rotation kind of dies down. So it goes from around 0.8, so the way that this rotation is kind of calculated is it's just an angle to the nearest group of particles nearby. And as we increase more and more selfishness into the system, this rotation dies down. The interesting thing about the target DOD, or the average delta DOD, is essentially that we kind of have 2 regimes. So in the black, what this represents is very close to that target, right? As selfishness increases, we go from this target DOD, this average domain, kind of being around 150. I keep saying DOD, but I haven't actually explained what that is. DOD is the domain of danger, so it's just the area that you own, right? So this average DOD essentially just means how close am I to the area that I want versus my actual area. And so you kind of have this, in this Couzin regime, there is roughly around 150 units squared is what the area is. In the selfish regime, it's around 250, 275 of what the actual area that the particles want to have. And then you kind of have a transition in between those 2. So based off of this, we can kind of create a score on how well a agent is behaving Cousinly and how well an agent is behaving selfishly. The way that I generated these scores was essentially taking, in the case where everyone's Couzin, what would the average rotation be? And in the case that everyone is selfish, what would the average rotation be? And kind of fitting a logarithm graph to that. And so you get, each scenario has its own score. So the Couzin score would essentially be, if your rotation is around 0.5, then you're scoring pretty badly in terms of a Couzin model. But if it's around 1, then you're scoring quite highly. Selfishness, on the other hand, is just recorded by how close you are to your DOD. So if you're very close to your DOD, or to the domain that you actually want, then you're scoring well selfishly. And if you're not close to this, you're going to be scoring pretty badly. So what we do is each particle is going to take their score, so they'll take a Couzin score and they take a selfish score, and they determine a probability to switch their current model. And so this switch is kind of defined by this nice 3D logarithm type graph. Essentially, you take your current score and your score for the other model and you fit it into this graph and you determine, should I switch my model or not? So that looks like that. And so the next stuff that I'm talking about is kind of a bit fresh, so it's not been made nicely, but this is kind of the results that's coming out at the moment of running this switching model. So they're switching based on these scores. What I started to see was we essentially get, so this graph here is looking at the proportion of particles that are Couzin over time. So they start at 50%, and you can see quite a sharp drop, which means everyone's kind of thinking, okay, it's a good opportunity to be selfish, and slowly but surely, it's kind of getting better to be Couzin the longer the model runs. And this number at the top is the target area that they're going for. as I'm increasing that target area, you kind of get these particles more and more quickly going to around 80% selfishness, or sorry, 80% Couzin. So they're kind of dropping their selfish traits and becoming more and more Couzin. So originally we thought, or I thought, this seems pretty cool. We have maybe some sort of stable structure that 80%, at this like 80% Couzin that everyone's kind of getting towards, and that this domain kind of tells you how quickly you go towards that stable structure. This is true, but it's not a nice stable structure, so it's a bit of foreshadowing. Essentially, what I've done is the simulations here are just going to be from that data that we've just seen, and what we get is, so this is for the 100 case. Essentially, it looks okay, and what happens is, I'll go to 142. As you can see, so in red is going to be Couzin particles, and in blue is selfish herd particles, but you can kind of see that guy is escaping. And I'll call it spinning off. So they've like spun off the group. And this is a bit of foreshadowing. But in the case of, as we kind of increase this DOD, what we can see is that these spin-offs happen more and more. So this graph here is, the way that these kind of plots aren't, so they're not 100% like the same axes, but these axes are very zoomed out, because as we kind of increase time, you'll see that the reason why we have this Couzin kind of 80% threshold is that everyone is kind of just leaving the group, which was not a cool structure to find. Everyone's just kind of escaping. Right, so what can be done? Well, as we saw in the 100 case, these spinouts weren't happening as regularly. So what I did was I slowed down the simulations and added a bit of noise. So I just slowed down how fast each particle is moving, and added a bit of noise. And I took smaller DODs. So this one is, they're aiming to have 0. So it's kind of, they're aiming to all be in one kind of group, but because they have to constantly move, they can't have that. And I think the dynamics are a bit easier. So again, this is kind of fresh data, so there's a lot of diagnostics flying around. I want you to just look in the top left, because everything else is just only things that I really understand. But regardless, we kind of get something that's a bit interesting. We're not getting that spin-off. We're getting structures, at least like stable type structures forming, where we have this milling, and even like counter milling. So you'll have like one group kind of milling one direction, and then on the inside, the group is milling the other direction. And sometimes these groups kind of join up, and there's some interesting dynamics going on there. This was for a target of 0, and I'll just let it skip ahead a bit. And so we see formation of 2 groups. What I've got here is for a target of 100. And this was this was pretty interesting as well. So essentially, as the group kind of stabilizes, you'll see that the Couzin particles want to stick on the outside and kind of form a hull around these, like a selfish group in the middle. And so you can even see that kind of party coming back into the group. Yeah, that's pretty much all I've gotten up to in terms of writing things out and doing it all properly. But obviously, this is kind of the stuff that it's, this is the goal that it's aiming towards, and this isn't obviously what I was going to show in the final talk, but yeah, that's kind of where I'm up to at the moment.
Alright, any questions on content?
I think I missed it, but why exactly why would an agent choose something selfish over Couzin with another selfish? Like, what's the motivation? biological reason
The biological reason.
and mathematical reason. So why would they pick one or the other? Is it like a because it's game theory, right?
Yeah.
So there's something you're trying to optimize somewhere.
Yeah, so the way that they're not optimizing the same thing. So we're kind of saying how well are you behaving Cousinly, and then rewarding, okay, if you're a Couzin particle behaving well in a Couzin manner, which is kind of looking at that rotation. So if you're rotating well, then you can stay being Couzin. And if you're a selfish particle who's got you've got a small area, then we're going to like reward that by you can stay selfish.
So is it like for a given situation, which option is the easiest to do?
Yeah.
Performant.
Yeah.
So I got it right. You've got an objective function, and if you are doing well with that objective function, you stick to it.
Yeah.
But if you can't optimize that objective function very well, you decide to go.
Go to try something else. Yeah.
Is there, just my own curiosity, is there a biological reason why that would be?
I think from some of the things that I've read, some of the like prisoner's dilemma type stuff played over multiple times where you're kind of picking like an overall strategy. Some of the strategies can be like, okay, well, it's worked well in the past, like I'll keep doing it. And then some strategies are, it's not working. Like whatever I'm doing at the moment, I'm losing a lot, so I'm going to switch to a different strategy. So that's kind of the motivation behind it.
But it seems like the score you're getting is how well you're following that strategy.
Yeah.
Which is kind of divorced from how well that strategy is doing.
Yeah.
Like a biological sense. So if you're able to avoid predation.
Yeah.
It's not clear that you're a Couzin particle happily sitting on the outside of the group, because that's the place where it's really easy to be Couzin.
Yeah.
There's also a place where it's really easy to get in.
Yeah. So that's. I have noticed that, and so I'm developing a second scoring system that I think will be aimed to be a bit more statistical in like how you get a score.
Something which is sort of biologically motivated.
Yeah.
As to
because
you could well imagine that if you had like if everybody was being Couzin, then in some sense, on average, they're doing really well at not getting eaten.
Yeah.
Whatever the thing is.
Yeah.
Whereas if everyone's being selfish, they're all trying to avoid getting eaten, but on average they don't do as well. That would be a Christmas dilemma type situation.
That was one thing that I'm
but I'm not quite seeing the game theory here, because I'm not quite seeing a payoff to being Couzin over being selfish.
Yeah.
In these things.
Yeah, I think we're trying to kind of. It's hard to like gamify some sort of single benefit for them both, because they're both independently biologically motivated in different ways. So like selfish.
What is the motivation for Couzin?
The motivation for Couzin was just like, this is an imitation of what birds might be doing.
So this matches what seems to happen.
Yeah.
Whereas the motivation for selfish.
Yeah.
That there's like an evolutionary reason
to do it that way. Yeah.
There's also biological reasons in terms of, for some reason, for some cases, some animals might do it because it promotes hunting efficiency.
And also, there's also like mating benefits and things like that. And yeah.
That's that. And those rules are inspired by whatever biologists came up with.
The thinking was just that it was Cousin's like a cooperator.
Yeah.
If you're behaving in a Couzin way, then you're aligning with your neighbours. You're all sort of, you've got the same objectives. In a sense, okay, their objective is not global in that they want to mill, but they're all sort of doing the same thing locally. They're on the same page, and so we get this global order. Whereas selfish individuals can have conflicting sort of movements, so they will sort of out of effect.
Yeah.
Yeah, but then I'm looking for like Chris's limits and advantage to whole grouping Couzin versus whole grouping selfish or
Yeah, I think
something like that. I'm not sure.
I think the point that we're looking at is when you talk about game theory, you're saying I'm strategy A or strategy B.
Yeah.
But you're not articulating the payoff
Yeah.
for choosing A versus B, right?
Yeah.
You kind of get a probability of switching, but that's not exactly a you don't have a payoff matrix. You don't
Yeah.
choose strategy A over this return if they choose strategy B. The person I'm playing against chooses strategy B.
Yeah.
Why is there a payoff to maximising that Couzin score? Why is there like a biological payoff or an evolution payoff? Or
I think it could probably articulate some degrees.
Yeah.
And it comes down to the figure that we had the 2D surface, 3D surface, 2D surface.
well, you're doing that good point, but Couzin produces like better mating opportunities or something like that. So you can score your chance getting even versus your chance to
Yeah,
your chance to
but I would suggest putting this as an equation.
Yeah.
But clearly that
Yeah.
two variables, distance and diameter. So write down that equation.
Yeah.
So I want to prefer Couzin because I can make it say with my friends.
Yeah.
I'm going to get eaten or I prefer some strategy.
Just going to say, I will open up to people who have comments on the presentation as well. It took about 90 minutes, so good
Yeah.
time again. And you survived about 8 minutes worth of questions.
Yeah.
So far.
So far.
Okay.
I wonder if you've thought about combining strategies, having individual agents combining strategies rather than switching between them. Maybe some sort of way in which you're involving the functions.
What do you mean by that?
Well, this model says I'm going to stick with this strategy if it's a good one, otherwise I'm going to switch.
Yeah.
In my mind, an alternative might be I'm not going to switch entirely, but I want to be a little bit Couzin, a little bit selfish.
Yeah.
Could
Yeah.
just go here. So
Yeah. Yeah. Kind of take some sort of average. Yeah.
I just wonder if you can let any thought or whether that be an interesting alternative.
I haven't. And the main reason, I guess, is kind of computation. So Couzin performs very quickly, whereas selfish herd, if you're calculating the Voronoi, kind of sells for 100 particles, and then each place that they sample, originally I had it at 16, so they count each particle is then running 16 new Voronoi tessellations to determine the next best area. So as much as, like, if you've got a 100% selfish model, it would be the same performance, but it does sound like a good idea. It's something that I would look at. I think part of a lot of the stuff that I was actually doing was trying to make the selfish herd run faster, because it just takes a very long time. So a lot of this data is over a lot of repetitions of the same kind of initial conditions, and it just takes a long time. So weeks at a time of just the same simulations running and just not really seeing anything. And that's mainly the selfish herd's problem. But yeah, I mean, that does sound like an interesting thing to look at. I am developing another scoring system, so it is good to hear like thoughts about how that could happen. At the moment, my thought was to kind of do it in like a statistical kind of way of figuring out in the static case. So all this data is kind of coming from the original static case. And so the way that I constructed these was a little bit kind of arbitrary of just picking like, yeah, that's a good number, make this score, but I wanted to do it a bit more statistically of what does it mean to be Couzin and what does it mean to be selfish. But maybe combining them is a good idea as well. So.
I've got another question about content. Way back at the start, when you introduced the viewing angle stuff,
Yep.
it makes sense biologically, and that's the way that Couzin did it. But do you know if it actually changes the qualitatively simulations that you get by having a blind spot behind you?
Yes, so it does for a lot of milling. It kind of, it lets the mill be a little bit more just kind of stationary in a way. When they don't have this blind spot, so you just put it to 360 to get rid of it. They kind of, sometimes you see this pattern where they're all moving in a line and then the person at the front kind of goes like, oh, I don't want to be at the front, and they kind of just track back to the back, and they, every now and again someone will do something like that. So it kind of does help the milling a bit, to kind of keep it in that regime, rather than kind of just falling back.
I guess it's also a cheap and easy way of making the dynamics a bit more fluid.
Yeah.
Because you tend to not overlap straight away.
Yeah, yeah.
In terms of that we've done at the couple slides forwards, we've done with the different perspectives. And now I'm just on the presentation style a bit now.
Yeah.
Is it kind of better to choose two directions that are a bit more aligned? Because now you get this weird thing where it's sort of saying, well, I want to go completely to the left, completely to the right. I end up wanting to turn around, but I can't do that, so I go slightly to the left. It's just a little bit confusing if someone doesn't really know what's going on.
Yeah.
Where am I going?
The reason why I kind of have it in there is to, like, I guess, really emphasize the fact that they can't turn very far, and that a lot of the time they do want to kind of go behind them, and then obviously they turn a little bit, and then now they want to go in a completely different direction. But if that's too confusing, then I can just change it to be a bit easier.
You
Like,
need to explain it better because it is very jarring.
yeah,
Someone's looking, I've got a blue vector plus red vector equals dotted vector.
and
No,
then
not. It's
all of a
exactly
sudden,
the opposite.
yeah,
Is it possible for you to maybe move those two groups a bit closer to the back so that the resulting is still the back, but make it biased in one direction so it's clear that it's like one way that's more convenient to go to than the other? So
what do you mean?
like move the two groups such that the dotted arrow is a little bit upwards, more to the top.
Yeah,
So that means it's kind of obvious, it's clearer that it's easier for
yeah,
the guy in the center to
yeah,
be
okay,
turning
yeah, to the,
anti-clockwise.
yeah,
than
anti-clockwise.
clockwise.
Maybe we should include a vector saying which way we pointed at the moment.
Oh, yeah.
I mean, you've got
Yeah.
a triangle, but it's
Yeah.
triangles,
It's got 3 heads.
yeah, it has 3 heads. I know it was a triangle as isosceles, but
Yeah,
if you added in the vector for the direction of current travel, because that's what's going on. Isn't it?
yeah, yeah,
So if we added in that vector, then it kind of makes more sense with something to do with a dotted vector plus a vector going in that way would make a vector go that way.
yeah.
Not sure. Is there like a simple enough equation to put next to this to explain it?
No. I had equations
It
and
would also help. You wouldn't need to say anything about it. but
yeah,
Yeah, if the equation was blue V plus vector.
Yeah.
It's
If there's something,
black V
if there's something
represents
simple
12
enough to do
together.
it.
yeah. It's, I can try, but every kind of equation I like originally had was just, it just gets very complicated, very hard to follow.
Is there a simple, presumably it's because it's an algorithm or something like that, can the algorithm be stated very, very simply, like a line or two, a couple of lines?
Again, not. I feel like the best way that I found is just like talking and visually kind of representing what's going on.
How much code is it to actually pull?
To do just the Couzin
Yeah,
or just the whole thing.
Just this decision as to which way we're going to go next.
Vectorized, it's pretty-
How many lines of code is it actually that you've written?
Probably 10.
Okay. No way to simplify it down to something that might be.
10 lines of code
This
is very
bit is
cheap.
V alignment in blue text. It's
Yeah,
V attraction red text.
yeah,
You try something, but I would avoid too much algorithm.
yeah.
That's going to traumatize the group.
And it's not the point, this isn't your model, it's someone else's.
Yeah,
The key is just that it's representative of the cooperative
yeah,
strategy.
Maybe just adding a vector pointing which direction we're going if that actually
Yeah.
gets apply that effect happens.
Yeah, if you just said the vector pointing in the direction you're heading, then you just say anything about it.
Yeah.
Then when you plot the final resultant vector, it kind of gives the audience a clue as to how you actually add them together.
Yeah.
I just had a couple of very simple things about presentation.
Yeah.
You've got lots of videos that are really cool, but also if you look at the length of your videos, there's one that's 5 minutes long, one that's 8 minutes long. You handled it quite well, but why have a 5-minute video and a 15-minute
Yeah.
presentation?
Yeah. Yeah.
If you can just show what you want to show, it'll be easier. You did say that the later stuff you were still working on, but this also applies to the earlier stuff. There were several diagrams where the axes weren't labelled or
Yeah.
ambiguously labelled, which could just help to have something written on the slides of people that are quite, not that one so much.
Yeah, these
So
ones.
so these
Yeah.
ones, what is the colour bar actually representing? And then the next one, there's no label at all, I think.
Yeah.
This one was,
No.
Just try and label everything you can.
Yeah. Yeah.
And,
These are all old graphs as well, so that doesn't help.
Does the Couzin selfish labels actually mean anything?
Yeah, is it when we target DOD for Couzin? Because
Yeah. Yeah. So the way that this is, before I actually ran it, we didn't know whether increasing the target DOD or not would actually affect how the Couzin particles would behave. It ended up having no effect, pretty much.
target DOD of the selfish particles.
Yeah.
Means selfish.
Yeah, so I didn't explain this quite well, but here you have 100% selfish particles. Here's like 50, and then here's 0. And as they're kind of getting more and more selfish, and as we increase their target DOD, this is measuring essentially how well they're milling, so how well they're performing Cousinly, and it's obviously degrading over time.
What you just said helps immensely.
Yeah, yeah.
Could you change from labeling as Couzin and selfish to rotational score and like
Yeah,
survival score?
in my actual thesis, doesn't say Couzin and selfish, but because I kind of just like cobbled this together last minute, I just
In fact, the title
Yeah.
should be the same as the title of the box would be bar, shouldn't it? So it should be, Couzin should be average local rotation border,
yeah,
Yeah.
and selfish should be average delta.
yeah.
And is it static if they're changing?
So what we mean by static is that the particles don't have the choice to change their model. So if you're selfish at the start, then you're selfish for the rest of the model, whereas later on, they're kind of assessing how well they're doing and changing their models. So that's,
You just got a mixed flock. You just
yeah, yeah,
There's no game.
yeah. There's no game happening here, yeah.
Any final points, questions?
I did have one other, just want to read my writing.
There's one at the back.
I mean, if go back to the game theory part.
Yeah.
Does it make sense to, like, you think about the motivation of selfish, I want to minimise my understanding of what my getting needed.
Yeah.
I want to sort of behave well as part of the flow.
Yeah.
It makes sense to use those metrics themselves as your reason to swap. Right? So if I'm behaving like a Couzin agent, I've ended up in a large domain of danger. I need to start worrying about that. I should swap.
Yeah, that's what the next scoring system that I want to look at. That was one thing that I did think about. Why am I punishing you for being, if you've got a bad DOD, why am I punishing you like selfishly for that? Maybe I should be rewarding you to say, hey, focus on your selfish attributes at the moment so you can get back to having some sort of reasonable selfishness score before you can be cooperative again. The main reason why I thought that was because as much as it was interesting to see that all the Couzin particles were on the outside, it was mainly because if you're on the outside, you're scoring badly selfishly, so you have to be a Couzin. And so that's kind of what I was the next kind of system is going to try and address.
I guess it's an interesting transition between having a simple blob where you've got Couzins on the outside.
Yeah.
And the selfish guys having
Yeah.
and just having the exploding case.
Yeah, yeah,
They can't contain themselves.
Yeah.
Anyway, which is my last question was, so if you have like a bit check model,
Yeah.
periodic boundary conditions because we're looking at quantum physics.
Yeah.
Obviously, periodic boundary conditions don't make much sense for birds.
Yeah.
But have you thought about the exploding case of what happens if you do a periodic boundary conditions and just get everything?
Yeah, so originally I was working with periodic boundary conditions when I was looking at the Couzin model. It's really hard to think about what a domain of danger would be in a kind of when there's periodic boundary conditions, and it starts to get quite weird and hard to kind of code what's going to happen. And then there was a lot of problems with like how close someone was to me in like different directions, and it was just getting way too much to kind of implement that. So then we just kind of switched it to trying to contain them in milling, and I think that's another reason why milling was the kind of better option, was because everyone kind of just stayed still, or if they were moving, then they weren't moving, you know, and just exploding off to infinity.
I believe the topologist probably.
Yeah, probably not.
I think with that, let's thank you for more time.